Welcome to Lecture 13. Here we'll continue our discussion of optimization models. And this week we're going to discuss integer linear optimization models. But first we're going to review the homework 12.2. That was your last graded homework assignment. So let's take a look at that one. So in this problem, the Seawharf restaurant wants to determine the best way to allocate a $1,000 monthly advertising budget between newspaper and radio advertising. Management's decided that at least 25% of the budget must be spent on each type of advertising, newspaper or radio. And then a marketing consultant developed the exposure ratings that we see here, 50 and 80, for the different types of advertising. So the question is, how should management allocate its $1,000 monthly budget between newspaper and radio advertising? So let's take a look at our model. Here we see our parameters defined. We have newspaper and radio. The exposure index, bring this out a little bit, per dollar is 50 for newspapers and 80 for radio. And then our minimum allocation is 25%. And of course, the advertising budget is $1,000. Here's our decision variables, which is the quantity of newspaper dollars, and the other is the quantity of radio dollars. And then we have total spent, and of course, total spent must be less than or equal to 1,000, which is the advertising budget. So that is a constraint there, right? This 1,000 and the total spend. And then we've got total exposure index is equal to the array of exposure indices times the array of quantities allocated. So this is our model for the Seawharf. Let's go up to data, then over to solver, and we'll see how we set this model up inside solver. So our objective function is the total exposure index. And our decision variables are B14 and C14, the quantity of newspaper and quantity of radio advertising dollars. So we're going to maximize exposure by changing the decision variables subject to our constraints. And the constraints here are that B14, which is the amount of newspaper dollars spent, is greater than or equal to 25% times our $1,000. So in other words, it's greater than or equal to $250, which is our minimum allocation times the advertising budget. And then likewise, C14 is greater than or equal to B8 times B9, or again, it has a minimum allocation of 25%. And that E14, the total amount spent, is less than or equal to B9, the total advertising budget. And our last constraint is that management wants the amount spent on newspaper advertising to be at least twice the amount spent on radio advertising. So that's going to be B14, which is the amount spent on newspaper advertising, is greater than or equal to 2 times the C14, which is the amount spent on radio advertising. So now we've got our variables set up, and we put our constraints in. We've got our objective function. This is going to be a simplex algorithm. Solver is set up. Let's go ahead and solve it. And so it comes back and tells us that it did find a solution. All constraints are satisfied. So we'll click yes. And we see that if we spend about 2/3 of our advertising budget on newspaper, then we'll satisfy the constraint. So about $667 on newspaper and $333 on radio. Okay. Let's close this. And next we'll go on to linear optimization models. So just as a review, a solver determines the optimal set of decision inputs to meet an objective. It's an excellent tool for determining the best way to apply resources to a particular problem. Optimization is an analytical method that narrows available options so you can choose the best potential outcome. Either a minimization of something you don't want to have much of, like cost, or a maximization of something you do want a lot of, like profit. So before we look at our optimization and setting up the model in Excel, we have to consider how many resources there are and how many are needed. So the amount of resources that exist are constraints. We can't go above that number of resources. And that can be things like the number of labor hours in a particular category. And likewise, what is the demand for these things? So, what is the supply of parts at a warehouse, and what is the demand for parts at a plant that you're going to ship the parts to? Second thing we need to consider is how many resources does each decision variable consume. So our decision variables are typically going to be quantities, and then you're going to have resource variables like the cost or the number of hours per quantity, and then that's going to become your coefficients in your constraint equations. And then another thing we need to consider is how much does each decision variable contribute to the objective. And again, let's say the profit, you get $2 profit from product A and $1 profit from product B. Those become your coefficients in your objective function. Integer linear programs are for problems that are modeled as linear programs with the additional requirement that one or more variables must be an integer. The objective is to provide an applications-oriented introduction to linear programming in Chapter 13. And that's what we'll start getting into in just a moment. But I'd also like to say that with integer linear programming, we have the ability to extend our optimization to a wide range of decision that might otherwise not be available to us by making binary variables and then applying them to conditions of co-requisite or conditional or K out of N multiple choice. And we'll see those as we get further along in the lecture today. But it really gives us a lot of flexibility in applying optimization to management decision problems. So we have a variety of integer linear optimization models. One is all integer, and that's all the variables are required to be integer. A linear programming relaxation of the integer linear program, and that results from dropping the integer requirements. Mixed integer linear, if some but not necessarily all variables are required to be integer. And then binary, and that's where the integer values may only be a 0 or a 1. And again, that binary is going to give us a lot of flexibility in applying optimization to a variety of management decision problems. So let's take a look at the integer decision making, and again it's going to be very similar to the linear optimization that we looked at in chapter 12 and that we just had your last graded event, problem 2 in chapter 12, with the addition that with the addition of the constraint that some of the variables or all the variables have to be integers. So when we're creating a solver model, the objective cell is the cell that you want to maximize, minimize, or set to a specific value. The decision variable cells produce the desired results in the target cells by changing. And then the constraints are limits on how to solve the problem. We create a mathematical model of this business scenario, and our objective function is then a mathematical formula that relates the decision variables and the changing cells in our solver dialog to the desired outcome. Now, we can also add or change constraints in our solver model. So the lower part of the dialog box is where we can use the add constraint dialog to add a new constraint. We can also select an existing constraint and click the edit or modify button so that we can change it if our model has changed. And just to refresh your memory even further, when we do run a solver report, we do have, well, when we do run solver on our model, we have the option of selecting a few different types of reports. One is the answer report, and we looked at that quite often, and that's the most frequently used report. It tells us if we have binding variables and things of that nature. Another is the sensitivity report. How sensitive is the model to changes in the values of certain variables? So now let's extend what we learned in chapter 2, and of course I just gave a quick recap of that, to add in integer optimization. And we'll start with Eastbourne Realty Company. And Eastbourne is a realty company that has $2 million available for the purchase of a new rental property. So let's take a look at the worksheet for Eastbourne. And here we see we've got the model for it set up. After an initial screening, Eastbourne reduced the investment alternatives to townhouses and apartment buildings. Each townhouse can be purchased for $282,000, and there's 5 of those that are available. Each apartment building can be purchased for $400,000, and the developer will construct as many buildings as Eastbourne wants to purchase. So we see some of these constraints in our model. The funds available is $2 million. All the figures you see here are in thousands in terms of the dollars that are costing. Townhouses available are 5. A management time available. So Eastbourne's property manager can devote up to 140 hours per month to these new properties. Each townhouse is expected to require 4 hours per month, and each apartment building is expected to require 40 hours per month. And so we see that the management time available is 140. And over here we see the price of a townhouse and an apartment building, and then the manager time for each, and then the quantities, the decision variables, here next to a purchase plan. And of course, we'll multiply the number of townhouses times the management time per townhouse and add that to the number of apartments times the manager time per apartment to come up with the management time that is used, and that has to be less than 140. Likewise, we're going to multiply the quantity array, if you will, or vector of number of townhouses and number of apartment buildings we buy times the matrix or vector of our prices for those items. So 282 and 400. So in this case, the total amount of funds used has to be less than the total of amount available. And then likewise, the number of townhouses we buy must be less than 5. So what we want to maximize is our annual cash flow. Now, annual cash flow after deducting mortgage payments and operating expenses is estimated to be $10,000 per townhouse and $15,000 per apartment building. Eastbourne's owner would like to determine the number of townhouses and the number of buildings to purchase to maximize annual cost flow. So let's take a look at our objective function right here. And that's going to be the sum product of B7, which again is our annual cost flows, the vector of annual cost flows, times B14 to C14, our vector of quantities for townhouses and apartment buildings. Likewise, we have to model our constraints. So here the funds used is again going to be a multiplication of our vector for the quantity of townhouses and apartment buildings times the cost vector for townhouses and apartment buildings, 282 and 400. And we see that in the sum product in the formula bar. For time, the time constraint, we again do a vector multiplication of our quantity vector, the number of townhouses and apartment buildings we have, times the time vector, management time per townhouse, management time per apartment building. And finally, the townhouses that we buy, which is going to be B14, that has to be less than our townhouses available. So we've defined our variables, but we might also add a couple of other constraints. The number of townhouses and apartment buildings we purchased must be non-negative. We cannot buy a -1 townhouse. Likewise, we cannot buy a fractional number of townhouses. So the number of townhouses and the number of apartments must be integers. So we have to add those in as constraints also. So this is our model. Let's take a look at the geometry of this problem. So here we see the geometry. The shaded region in this figure is the feasible region for the linear programming relaxing the integer constraints. And with that particular relaxation, in other words, we could buy fractional amounts of these, the optimal linear programming solution is going to be point B. And that would be 2.479 townhouses and 3.252 apartment buildings. And then the maximum value of the objective function is going to be $73,574. Unfortunately, Eastbourne cannot purchase fractional numbers of townhouses and apartment buildings, so further analysis is going to be necessary. In many cases, a non-integer solution can be rounded to obtain an acceptable linear solution. So, for instance, a linear programming solution to produce a scheduling problem might call for the production of 15,132.4 cases of breakfast cereal. And the rounded, pardon me, and the rounded integer solution of 15,132 would probably have minimal impact on the value of the objective function. A near optimal solution is going to be satisfactory. However, rounding may not always be a good strategy. When the decision variables take on small values that have a major impact, so obviously in the cereal example we had a large value, and so a fractional amount isn't going to make much difference. But here we're talking about small values, 2 townhouses or 3 apartment buildings. So their fractional values have a major impact on the value of the objective function or the feasibility. So an optimal integer solution is needed. And we'll see how we do that when we take a look at solving. Okay, let's open up our worksheet here. So we have our model, and let's construct our solver solution. Move this over here. So as we do with our linear programming, we set our objective function, and in this case it's to maximize cash flow, which is the formula in B17. And we're going to do that by changing our decision variables, which is the vector B14 to C14. And then we have our constraints added in, which are the values that we went over earlier. F15, the total funds used, is less than total funds available. management time used is less than management time available, and townhouses is less than 5. So this is in our vector F15 to F17 less than or equal to G15 to G17. Now we also have that problem that, or not problem, we have that additional constraint that we have to have an integer number of townhouses and an integer number of apartments. And we can see that we have that in our constraint B14 to C14. That vector must be equal to integer. So let's see how we add in an integer variable. It's easy enough to pardon me, put in our normal relational constraints, less than or equal, greater than or equal. So let's put in the constraint that the number of townhouses alone must be integer. So we'll put in B14 and we'll say int. And we'll go ahead and add that in. And now you can see we've added that in as an integer constraint. B14 equals integer. So when we select our relational operator, the relational operator we select is integer. Since I already have this constraint in our subject to constraints list, I'm going to delete it. We use the simplex method, and we'll go ahead and solve this one. And it does come up with a solution. So we'll click OK. And the optimal solution is for us to make to purchase 4 townhouses and to purchase 2 apartment buildings. And with that, we come up with our optimal solution with 70, showing that we make $70,000 for this particular optimization. So this is how we add integer constraints into a optimization model. Okay, so we'll close this one. Don't save. Okay. Next, we'll look at some more integer optimization problems in Excel. And the worksheet sheet formulation, let's see, for integer linear programs is very similar to what we did with linear programming. The only thing is we added in a constraint where we selected int as our relational operator, if you will. So the big difference is we set up our model just like we would for a linear programming, and then we add in integer constraints for the variables that must have integer values. And obviously many times we're going to have that kind of constraint in the business world. So we can also demonstrate the Excel solution of an integer linear programming by showing how solver can be used to solve these type of problems, and we did that with the Eastbourne Realty problem. The worksheet with the optimal solution was what we found out, and we got $70,000 as our optimal amount for that. So we've taken a look there. And we can also look at a cautionary note about sensitivity analysis, and that's often more crucial for integer linear programming problems than linear programming problems. A small change in one of the coefficients in the constraints can cause a large change in the value of our optimal solution. So that's just something we need to keep clear in our minds. And in fact, let's go ahead and look at the sensitivity analysis for this particular problem. So we'll come up here, go to solver, and simplex. We'll solve it. And let's look at what we have. None of our constraints are binding. So we have slack in all of our constraints. So that's an interesting finding in itself. We do see that we have integer added in as a requirement for our variables, and our final value of 70,000 is the maximum amount for our particular problem here. Okay, let's go on to look at binary variables, and this is a way we can incorporate a large variety of management issues and problems that they need to optimize with our solver tool that we have in Excel. So one example is going to be capital budgeting problems. And this is a binary integer programming problem when you're choosing among possible projects, for example. And the objective function is to maximize the net present value of the capital budgeting projects. So as an illustration, pardon me, we'll look at the ice cold refrigerator company, and they have several projects that have varying capital requirements. And of course, like most businesses, they don't have unlimited capital, so they have to maximize a scarce resource, and management would like to select the most profitable set of projects that it can afford. And the estimated net present value for each projects, the capital requirements, and the available capital over a 4-year period are shown in this particular table. So let us define the 4 project decision variables, or the decision variables for, and they are going to represent the projects. P is the plant expansion project. It takes on a value of 1 if the plant expansion project is accepted, and 0 if it's rejected. W is the warehouse expansion project. It takes on a value of 1 if that project is accepted, and 0 if it's rejected. M is equal to 1, that's the machinery project, and that's 1 if it's accepted and 0 if it's rejected. And then the last one is the product research project. and that's going to take on a 1 if that's accepted and a 0 if it's rejected. So we have 4 constraints in our problem, and 1 for the funds available in each of the next 4 years. So we have a binary integer linear programming model that we see here, and we want to maximize the return of 90 times project 1 plus 40 times project 2 plus 10 times project 3 and 37 times the last project. And we get those from the plant expansion net present value, the warehouse expansion net present value, the new machinery net present value, and the new product research net present value. And here we see the plant expansion capital cost for year 1, warehouse expansion cost for year 1 capital requirements, and over on the far end we see the total capital available in year 1, year 2, year 3, and year 4. So that's where we get the coefficients that we use in our objective function and the constraints. So our model is that we want to maximize this objective function subject to these constraints. So the year 1 capital requirements is this, the year 2 capital requirements is equal to this, and that must be less than the available capital that we're going to have projected in those years. So we have that for each one of the 4 years. And then we also have the constraint that our project must take on values between 0 and 1. Okay, so let's see how this model translates into Excel, and then how we take that Excel model and put it into our solver function. So we'll bring up that worksheet, which we see here. So here are the various amounts we looked at in that table that management gave us, net present value, and what we want to maximize is the net present value to us. And it's going to be subject to the constraints, capital available, we see here on the far right. So in a sense, we just replicated the table we saw in PowerPoint in Excel, with the year 1 capital requirements for each of the different projects, year 2, year 3, and year 4. Our objective function is going to be C6 through F6, which is our net present value vector for each of the projects, times C20 through F20, which is our quantity or our decision variable vector for each one of the projects. And of course we can the quantities can only be binary, so that's another constraint. So we put our constraints in here. The year 1 constraint is the vector of the year 1 cost, capital cost, for each one of the different projects. So it's the year 1 capital cost vector for our projects times the quantity vector for our projects. And of course, again, I'll reiterate, the variable must be binary. In other words, we can each one of those variables in the projects can take on a value of 0 or 1. And likewise for the other projects that we put or the other years for our capital budgeting. So let's translate this into solver. So we go up to data, then over to solver, and we're going to maximize D16. That's our net present value. We want to set, that's our objective function, and we want to maximize that. We're going to do that by changing our decision variables, which are the which projects we decide to go forward with. So that's going to be a 0 or a 1 for our decision variables, and so that's what we're going to change. So we have the option of making it a 0 or a 1 and then testing all the combinations and seeing which one gives us the maximum return. We also have our constraints. Let's take the bottom one first. So we have B24 to B27, and that's the vector of capital expenditures that we make based on our selection of projects for year 1 to year 4. And that has to be less than the funds available from year 1 to year 4. So that's our other vector, C24 to C27. So B24 to B27 must be less than or equal to C24 to C27. Then we also had that constraint, and I brought it up several times, that our decision variables are binary. They can only take on the values of 0 and 1. And we see that here in this constraint. The vector C20 through F20 is binary. Pardon me. So let's go ahead and see how we add in a binary constraint. So we'll say we want C20 to be binary. So we select bin and add it in. And now we've got C20 equal to a binary constraint. So I'll go ahead and delete that one since we already have it in place. And we'll run it. So I just as placeholders put zeros in for each one of our binary, our decision variables, which are binary. So let's go up to data and solver, and we'll solve this one. And we can see that we then get 1, 1, 1, and 0. So basically I went back and changed these to 0 so we could see that it actually did make a change to optimize things. So again, we have all zeros in there now, and then we come up and we do solver, and we run this, and voila, we come up with a solution. And we now have the optimal solution, which is going to give us a maximum net present value of $140,000. Okay, so so again, with our binary variables, we're going to have the ability to apply it to what are known as fixed cost problems also. And we'll take a look at these in part 2 of the lecture. I do want to keep these at under an hour just as a courtesy to YouTube and also to you guys, so you don't have to sit for a solid block of 2 hours and listen to something. So I'm going to go ahead and stop this part 1 video, and then we'll pick up here with the part 2 video. Okay, thank you, and I'll see you in part 2 of chapter 13.